we remember on the router, there can be static routing that is configured. It's a common misconception that, boy, we would never do static routing. Why would we do static routing when we can have the routers do dynamic routing? Well, keep in mind, if you have what is called a stub network, let's say we have router 1 here, and this router connects into an area of the network, and behind this router are just a couple of segments that have no other way to get to the rest of the world except through R1. We call this a stub network. And with this stub network, we can go ahead and configure a simple default static route to get everyone to the rest of the world. So, yeah, dynamic routing is wonderful, but we are still going to have plenty of environments in which we have static routing used. Dynamic routing, of course, we allow the routers to exchange information in order to fully populate those routing tables that we utilize. Dynamic routing protocols are indeed going to be categorized into 2 categories, and one of those categories is called interior gateway protocols. And these are protocols like EIGRP and OSPF that run inside our organization. We take our organization and we may indeed take prefixes and advertise them out to the internet, and this is done with what is called exterior gateway routing protocols, and there's only one of those in use today, and it's called BGP. So there are several options for interior gateway protocols in our organization, and then there's only one option for exterior gateway protocols, and that, of course, is the border gateway protocol. So what are routers tasked with? Well, they're tasked with discovering remote networks, maintaining a routing table of that information, choosing what is the best path to get to a destination when there are multiple paths, and if one of the paths or both of the paths go down, what path do we take? Discovering a new path to the destination. Now, earlier I pointed out to you that we have our interior gateway protocols and we have our exterior gateway protocols. And what really determines if we are going to use an EGP or an IGP is whether or not we're in the same autonomous system. Yeah, the term autonomous system is used to describe a particular network. And notice there are autonomous system IDs, which will identify organizations for BGP to be able to move traffic between them. You know, it's interesting. So these, like EIGRP, OSPF, RIP, these are protocols of our company, right? So they're protocols of our company. BGP is the protocol of ISPs and the internet. Now, when you say that, you say, all right, well, if ISPs are the only ones that are going to run BGP, why would I even care if I don't work for an internet service provider? Well, keep in mind, huge companies like Cisco, they are going to go ahead and run BGP because they want to get through the ISPs the information to their biggest customers in the most efficient manner possible. Now, we don't focus on BGP in this class because this is not a class targeted at, service providers and supporting really big information environments. What CCNA focuses on is interior gateway protocols that we are going to run inside of our organization. Now, the first generation technology that came along was distance vector routing protocols. In fact, it was RIP version 1 that first came along. And RIP version 1, it was true distance vector in that it just looked at how many hops away a particular destination was, and it looked at the direction, also known as vector. You can think of airplane here with the famous scene, "What's our vector, Victor?" And then to further complicate things, one of the pilots was named Roger. So they would say, "Roger, Roger." And then I think there was clearance, Clarence. Well, anyways, you get the idea. Vector is direction. So RIP said, look, we're just going to measure things by how many router hops away and in what direction you are. Direction would be dictated by the particular interface out which you reach that particular destination. Distance vector routing protocols were improved a bit when RIP version 2 hit. So RIP was re-engineered into a version 2. It was still distance vector, but as you might guess, RIP version 2 did feature some improvements over RIP version 1. Then link state routing protocols were invented. This is really our second generation technology, and OSPF and ISIS were in the second generation of improved operation. Then Cisco came along and said, we're going to take the best features of distance vector and we're going to marry them with the best features of link state, and we're going to create an advanced distance vector routing protocol called EIGRP, Enhanced Interior Gateway Routing Protocol. Do you know that as of this month of this year, February 2013, Cisco has opened EIGRP up to the public? That's right. It used to be a proprietary Cisco routing protocol, and for purposes of your exam, I want you to remember that. It is Cisco proprietary, but as of this month, that is no longer true. Cisco has opened up EIGRP for the entire world to utilize and even modify on their particular own equipment. Now, one of the important distinctions between all these interior gateway routing protocols is how will they figure out what is the best path? Now, we term this the metric. Yeah. One routing protocol will use a specific metric or measurement when it is trying to figure out the best path compared to another routing protocol. For example, RIP will utilize a metric of a hop count. Yep, how many hops away is a particular destination? OSPF will use a metric of cost, and cost is based on bandwidth. So OSPF would look at this and say, well, I'm going to choose this path because T1 links are superior to 256K links. And then there's EIGRP, which can use all four of these if you want, but by default will use bandwidth and delay values as its metric to determine what is the best path. RIP starts to look a little scary to us, doesn't it? Because if it uses simple hop count for a metric, it would consider this the way to go, and this is so much more pathetic of a path. So yeah, RIP really does look scary to us in its simplistic operation. Now, what happens if your routing protocol, if your router, is running multiple interior gateway protocols? What if it's running RIP and it's running EIGRP? Wow, and I've seen this slide a million times and I just noticed that there's a typo there. That's amazing. So that's EIGRP, of course. Well, if your router, let's say router A, is running both of them, and both of them say, hey, I know how to get to location X, Who is router A going to listen to? What routing protocol should it listen to? Should it listen to EIGRP or should it listen to RIP as far as how to get to destination X? Well, the router uses a value called administrative distance in order to solve this question. The lower the administrative distance of the routing protocol, the more believable it is. Yeah, great job. So it's like a golf score. So EIGRP is believed or listened to by router A, and the RIP information is not used because of the worst administrative distance score, or a worser or lesser administrative distance score. So pretty interesting. Now, do you think Cisco based these scores on sophistication? Yes, indeed. That's exactly what they did. They said, look, EIGRP is just better. In fact, I hate to pick on RIP, but it's better in every way than RIP. So sure enough, EIGRP gets a lower administrative distance score, and it is the routing protocol that is believed when it comes to getting to a particular destination out there on the network. Now, distance vector routing protocols. We said they were the first generation technology, as evidenced by RIP version 1. And we said that this first generation technology was very simplistic. It would have a vector, hey, in which direction are we going to go? And it would have a distance, a hop count that it would measure. Something else that distance vector routing protocols do, as we can clearly see in this awesome graphic, is that they periodically take their routing tables and just send them back and forth to each other. Now, this looks pretty bad, right? This looks pretty darn bad. And think about this fact. This happens regardless of the stability of the network. Oh my goodness. So your network is completely stable and your devices are going to be periodically, for no reason whatsoever, sending their routing tables back and forth like this. A lot of people say, yeah, RIP is an extremely chatty protocol. Yeah, I'll say RIP is an extremely chatty protocol, all right. It is sending its entire routing table to all of its neighbors periodically, even if there is no change whatsoever in the network infrastructure. So the routing tables have the destination prefixes, and they have a simple hop count for the metric in the case of RIP. Let's analyze this. 10.4.0.0 is over here, and from router A's perspective, that is 2 hops away. That's the distance. And what's the vector, Victor? Well, that is the serial 0 interface. So here's the 1 hop, here's the 2 hops away, and go the serial 0 interface direction. Now you see, router A assembled that information by listening to what router B told it. Distance vector routing protocols are what we call routing by rumor. Yeah, this device thinks it knows how to get to a particular destination based on the information that router B gave it. This is indeed the concept of routing by rumor, folks. And you know what it reminds me of? It reminds me of a game I played in elementary school. The teacher gathered us all up and got us in a big circle. And then that teacher had one student whisper a phrase to the other student in the circle. So the teacher said, the phrase is, next Tuesday, the starry sky will be beautiful. That student whispered it to the next student. That student whispered it to the next student. It was amazing. By the time it went all 20 of us, by the time it was whispered to all 20 of us, and the statement got back around to the teacher, it was completely different from the original statement. I mean, completely. It was like, on January 1st, it'll be sunny and partly cloudy. When the original statement was, next Tuesday night, it will be a starry, beautiful night, or whatever, right? I mean, it was completely different. This distortion of the truth reminds me of exactly what can happen in a distance vector routing environment. Bad information can make its way in here, is passed to here and believed, is passed to here and believed, and can corrupt the environment. This is the exact opposite of what link state routing protocols do, like OSPF. OSPF is going to not rely on the information given to it by other neighboring devices. It's going to build its own picture of what the network is based on a database worth of information that is reliable. And of course, we'll talk about that more later on. So, updates come in. The router processes these updates, updates its routing table, and sends this information to the next device, which updates its information and, of course, sends it on. Now, we're going to come to what is probably the funnest depiction, the most remarkable section of the course, at least for today. And that is, I want to show you the nightmare that can happen with a distance vector protocol. I want to show you that corruption of information and just how bad it can be. And then we'll show you fixes that were engineered for this problem. So let's look at how bad things can get in a distance vector environment. You're going to love this. And I really want to send a big thank you out to the graphics department here at stormwind.com. As you've noticed, as we've moved throughout this course, the graphics department is unmatched compared to any other training organization that I've ever seen. So big thank you to them. All right, watch this. So here we have a happy little network. Woo, happy, happy, everybody's fine, everybody can reach everybody. All of the information in the routing tables is valid. You could go in and you could do it line by line and check it. Just trust me, everything you see here is perfectly valid. Well, watch what happens. Router C loses its link for the 10.4 network. See that? Look at the cable, it's frayed, it's broken. There's a broken cable right there. So what it does is, in its own routing table, it says, okay, I can't get to 10.4. Now, the first issue with these first generation distance vector routing protocols is that due to a slow convergence, router A thinks it can still get there, and router B thinks it can still get there, wherever the entry is. There it is. So these devices are still foolishly sending traffic through the environment. So first problem, slow convergence. Yuck. Now watch this. Based on how distance vector routing protocols worked, this device is going to send its routing table, right, over to C, And notice it has an entry for 10.4 that says, hey, it's out my serial 1 interface and I'm 1 hop away. So router C says, oh, great. I now know how to get to 10.4. It's serial 0 is the direction and it's 2 hops away. Uh-oh. Watch what happens. This device sends an update to router B. Router B goes, oh my gosh, it turns out that I should go out serial 1 towards 10.4, but it's 3 hops away because router C just told me it's 2 hops away. I'm going to send this to A. A says, wow, 10.4 is available, and it's 4 hops away. Oh boy, you see where this is going. A updates B, B updates C, and they're all thinking that 10.4 is available, and they are all incrementing the hop count to get to that particular network destination. The engineers of RIP saw this and said, we're geniuses. We've got a fix. And you're not going to believe the fix. They said, we'll just define a maximum hop count. That'll take care of it. So they said, look, if this starts happening and we get up to 16 hops, consider the route dead. Consider it unreachable. So the first safety mechanism, if you will, that they put in place with RIP was a maximum hop count. How'd they come up with 16? Well, I imagine some smart engineer types got into a room and said, look, RIP is for small networks only, so it's really inconceivable to us that we would ever have an environment where there'd be more than 16 router hops wide. I mean, after all, this is designed for small networks. So they picked that number. By the way, did you notice something else that could happen in this environment? At one point, router B thought the direction was to C, and router C thought the direction was to B. Uh-oh. This creates a routing loop. Router B sends the information and data to C. C turns around and sends it to B. And this continues over and over and over again. B sends to C sends to B, and it just continues endlessly. So another security mechanism they put in place that made such common sense was called, got a really cool name, Split Horizon. Split Horizon says, look, if I generate an update, if I send out an update about a network that I possess, I am not going to listen to that information coming in from that interface. Oh, this makes such perfect sense. This is how we humans work in communication, right? When I walk up to you and I say, Dan, you are the smartest person in this class. Do we have a Dan in class? Hey, that worked out great. We have 2 Dans in class today. Dan, you're the smartest person in this class. Dan doesn't look at me and go, Anthony, I'm the smartest person in this class. Although it might be good for Dan to do that for his confidence, that's not how we communicate. So, Split Horizon says, look, if I send an update out an interface, I'm not going to listen to that same update coming in on that interface. Now, there is one exception to Split Horizon, and that's called Poison Reverse. What is Poison Reverse all about? Well, it says we will accept an update in on an interface if it is indicating that the network is down. Yeah, see, when this network fails, we poison the metric to 16 and say it's not reachable. We will listen to that coming in the same interface we sent it. So poison prefixes can go and be an exception to split horizon. As we can see here, poison reverse overrides split horizon. We will listen to poisoned prefix information. You know what else they did that was brilliant? They said, look, when something fails in the infrastructure, instead of letting our network become unstable, especially in the case of like an interface going down and up and down and up, we call this a flapping interface. RIP says, you know what? We're not going to listen to anything about that prefix for a certain period of time. Oh, what a nice feature. It's called the hold down timer. And RIP just stubbornly says, look, there may be a problem with this prefix. And as opposed to becoming very unstable, we're just not going to listen to this particular information for this prefix for some period. Pretty cool. And this really does help with a situation like you see on screen, where we have a network going down and up, down and up, down and up. And by the way, this is what interfaces do. This is what interfaces do when they fail. Interfaces just don't fail. They tend to fade away. And that means they flap. They go up, they go down. They go up, they go down. And that's obviously a bad thing. By the way, when the network first goes down, we want to make sure everybody knows that right away. So they invented the triggered update for RIP. Yeah, to improve RIP, they said, look, if something does happen, don't wait to tell everybody. Tell them right away. So folks, all of these mechanisms, poison reverse, hold down timers, split horizon, a maximum metric, all of these forces work together in a distance vector environment like RIP to make sure your routing is stable and healthy and happy.